So now we continue with seeing again at how dislocations are generated by irradiation. But thanks to the fact that we have now gone through the dislocation structures, we can understand what's seen much better than before. And if we look again at this movie, which has been shown since the beginning of the course at least a couple of times, you saw how you have a heat spike, which generated the complex heat spike region. But after the cascade cooldowns, almost everything recrystallizes. But if you follow closely what happens when the crystals almost perfectly regenerated, you see that there are some line-like defects here. If you look, for instance, here, you can clearly see that there is some sort of a network of defects in here along lines, which we now understand definitely is some sort of a dislocation structure. These other things here may or may not be dislocations. They are much smaller. Most likely at least these structures are at some point defect agglomerates. So one can zoom in on these atomic coordinates and look at what happens. And at first it's actually better to look at atom or defect coordinates to understand on an atomic level what happens before one goes to this Oviedo analysis of dislocation lines. This is one example of a 50 kV copper irradiation of copper, the final defect. So here they were analyzed with Wigner-Seitz defect analysis, which means that an empty lattice site, empty Wigner-Seitz cell is labeled a vacancy, and one with two atoms and interstitial. And you see that on one hand we have here something which is not for sure a dislocation because it has a very complicated structure. On the other hand, here we have an interstitial cluster, which clearly we have a platelet, a slightly tilted platelets of interstitials, which is well localized. So this quite clearly is an interstitial cluster which is surrounded by a dislocation. One might say that it's a sequence of edge dislocations on lines next to each other, although they, as you see, the structure is somewhat disordered. So it's a dislocation loop, but not a well-ordered dislocation loop. Well, how are these formed? There are a few mechanisms by which ordered interstitials can form. One of those is if when you have the heat spike, when it cools down, sometimes you form like a neck in the heat spike like shown here. And then if you have extra atoms here, this neck may recrystallize. Here it has recrystallized before these atoms have time to flow back to the center of the heat spike. So then you have some extra atoms. Here you say they are still in a disordered configuration, but after a while they form a fairly well-ordered configuration, which is then a small interstitial dislocation loop. And these have been seen in basically since the 1990s. And already in the 1990s, Roger Stoller and David Bacon did many simulations like this and analyzed the dislocation character. In that case, it was quite tedious, done from the atom coordinates. Now this Oviedo analysis makes it nowadays to do much easier to do this. There is also another possible explanation to this formation of interstitial cluster, which is known that the pressure wave leaves behind a number of defects, but even then the pressure wave needs this isolation of the liquid to ensure that the interstitials stay there and don't recombine with the vacancies. The vacancy clusters, they are sometimes quite disordered as in the previous example, but sometimes also pretty well ordered, like here you see a almost perfect vacancy platelet on a single structure. And this is right after a cascade. If one has some longer time scales, then it's quite clear that these disordered vacancy clusters would reorganize towards a more well-ordered dislocation loop. Of course, it depends on the ambient temperature, how efficiently this happens. And one specific example of how this can happen is the formation of stacking fault tetrahedra. And stacking fault tetrahedra is a special tetrahedron of stair rod dislocations in FCC metals, which have been seen experimentally many times in irradiation of FCC metals. sometimes already at 20 kelvins when there isn't any significant defect migration expected. And so this is the basic structure, and it's a vacancy-like defect. That is, one can imagine that it forms that you remove one plane triangle of vacancies, and then you let the atoms above it collapse towards it, and then you have this set of four triangles surrounded by stereo dislocation loops, where there is a minor deficiency of atoms on all sides of the pyramid. In principle, one could have also the opposite, an interstitial type stacking fault tetrahedron, but that would have an extremely high energy, and it's believed that all stacking fault tetrahedra are vacancy-like. But anyway, it seems that sometimes you observe indeed also in MD simulations the formation of stacking fault tetrahedra. This was a simulation wherein copper one saw perfect stacking fault tetrahedra. This is analyzed in terms of the vacancies, so you see it, that these vacancies which are surrounding this tetrahedron. And in bigger ones, quite often you see that you get something which resembles an SFT but has a complicated structure. But then after it does an annealing, for instance, in this case it was 1 nanosecond annealing at 800 Kelvin, the vacancy is indeed reorganized towards something which is not quite but an almost perfect stacking fault tetrahedron. In a TM experiment, this kind of thing will probably look like an SFT with a slight disorder on one side. Well, one more thing worth mentioning here is that when you are near surfaces, this flow of atoms to the surface and formation of adatom clusters like this picture here, you formed an adatom layer, double adatom layer, when the heats quite flow to the surface, and the atoms were flowing to the surface, but due to this, when you have flowed atom to the surface, you have many more vacancies left behind the surface than interstitials, and this leads to then to a complex vacancy-like network, which, however, an annealing might very well form dislocations. And nowadays, with DXA analysis, one can analyze that in much more detail. And this is analysis of defects formed in a tungsten foil by two overlapping 150 cascades. And then here you see that you have formed a large vacancy loop, but then also a dislocation network surrounding the region where atoms were displaced to the surface. The details are not important for this course. This is just to illustrate that by combining this atomic defect analysis and the DXA analysis, one can really get a very good picture and also quantitative analysis of what kind of dislocations are formed in collision cascades. And now we'll repeat intentionally one of the animations from earlier in the course where you had a heat spike here, which reformed. Now we can understand better what's here. So here you see that here you have one of these disordered stacking fault tetrahedra. Here is another one, so the which are formed, and here is a perfect partial mixed dislocation loop, which also in a Wiener sites analysis is a fairly well defined shape. This is typically something, this is a molecular dynamics time scales. If I would then anneal this at higher room temperature, slightly higher temperatures, it's quite certain that all these dislocations would have a geometrically more simple and more symmetric shape. Well, so we also mentioned that dislocations can move easily, but this is an issue where actually the MD simulations can be quite misleading. If you do MD simulations of a perfect crystal and a dislocation in a perfect crystal, it looks like some common types of dislocation have mobilities with the migration activation energies of the order 0.01 eV, which is very, very low. And this would mean that they would move at room temperature way below room temperature quite fast. But on the other hand, experiments indicate much higher activation energies. For instance, 1 eV for 111 loops in iron. Um, and the reason to this is actually not for sure known, but there seems to be a fairly strong consensus, several MD simulations which support the conclusion that the reason is that in reality the interstitials are always bound to impurities like carbon and oxygen, which are always present in metals. The rule of thumb is that unless your metal is a ultra high purity metal which costs an absolute fortune, then you have at least something like 0.1% carbon or oxygen impurities per metal atom. And if you look at a dislocation which has at least hundreds of atoms inside it, means that the dislocation is practically almost always has a carbon or oxygen nearby, and practically always is then interacting with the carbon or oxygen impurities. And this binding energy of the impurity is order of 1 eV. And this slows down the dislocations because to move they need to drag along, either separate from the carbon or oxygen or drag them along. And this means that the inherent pure dislocation mobility in practice cannot be observed. But I emphasize this is still ongoing research, and it's not fully certain if this is the complete explanation. Well, one thing which on the other hand is definitely true is that alloying elements can slow down dislocations. That's actually one of the main reasons why metals are alloyed, is that by slowing down the dislocations, you increase their hardness and reduce their flow, their plasticity, which for mechanical properties at least is generally a desired quantity. Just a very, very simple example is that regular gold, you probably have heard that if you are completely pure gold, 24 karat gold, it's actually an extremely soft metal. You can modify it by hand. Same true is with lead. And because of that, gold jewelry is never sold as pure gold, but it's sold with 18 karat or 14 karat or something, where you have then typically silver as the other element, and having this silver as an alloying element of gold then makes this gold much harder. Here is a more recent example of that. The part of the explanation why stainless steel are hard is that stainless steel always contain at least around 10% chromium, and this was showing how with chromium concentration the mobility of interstitial dislocation loops slows down when you go already from to about 3 or 4 or 5% chromium concentration. And this is also very important for understand the buildup of radiation effects in steels. Well, and then also obstacles, precipitates in metals slow down dislocations. And this animation here shows how you had an edge dislocation in iron and an cementite precipitate, iron 3 carbon precipitate, and this see how when the dislocation comes to a precipitate, it slows down, it almost bends over, but then it gets eventually loose and speeds up again. And this actually keeps repeating. Well, in this simulation, we're simply straining it so it was run many times over, but you see that the same process repeats itself. And this is just one example of many, many simulations which are nowadays going on to understand how dislocations created by irradiation or otherwise interact in materials. This example here is quite important actually, because real iron quite often does contain cementite precipitates or cementite slats. But this is something where the knowledge is by far not complete. In fact, one can summarize the state that we know that there are things we don't know. Relatively simple cases like this have been studied and are fairly well understood, but then there appear to be many dislocation interactions and more complex geometries where there is not quantitative understanding of what goes on. This here is of course a simplified geometry because you have straight edge dislocation, and which is exactly in the same plane as the cementite precipitate, so it's in many ways a very simple case. Experimentally, what has been observed already a good while ago is that when you irradiate metals for a long time, you first increase the dislocation, but then if you strain the metal, the dislocations somehow become mobile and introduce what's known as channels of very pure crystal. So in this old image here, these dark areas are regions which have a high concentration of dislocations, and then somehow, due to this dislocation channeling, a region of the crystal has been almost completely cleaned of dislocations, even though everything was irradiated. Okay, now I emphasize that this channeling, dislocation channeling, has nothing to do with the ion channeling we discussed earlier in the course. And this is believed to be very important for understanding how those radiation damaging metals. But this is one more of the effects that are not fully understood. Discrete dislocation dynamic simulations have been able to reproduce this effect, which is also known as plastic flow localization. In these simulations, the author stated that the explanation was that these locations are pinned by other defects, but then some mobile dislocation can unpin them and sweep away them, which leads then to this channel of high quality crystal again. But definitely there is still many things to do to understand this completely. So overall, as a finish of this dislocation section, I'd like to summarize the current, speaking now in early 2021, understanding of how well irradiation and dislocations are known. So, first of all, it's definitely well known that the irradiation generates dislocations both directly in heat spikes and then even more by irradiation. So this is known. And this is also seen both experimentally and simulation. While the simulating dislocation, one gets different results with different MD potentials. Here there has been lots of progress going on, and the machine learning potentials will almost certainly give additional major advantage in the next 5 or 10 years. So this is sort of state is pretty good, but there is still things to do. But then dislocations are known to be mobile. This has also been seen directly in experiments, and this is the key reason behind the plasticity of metals. But this mobility is slowed down by impurities, alloying elements, and obstacles. This is in complex veins that are not yet quantitatively known. I could say that here knowledge is qualitatively, we know this happens, but in most cases we don't have enough reliable numbers to be able to predict this quantitatively. When you irradiate metals for a long time, you build up dislocation concentration, which hardens metals, at the same time makes it more brittle, but everything that's going on is definitely not understood. And there is a range of work combining molecular dynamics and discrete dislocation dynamics underway, attempting to do that. But this is sort of where the current work is strongly ongoing, although there is still definitely work going on at point 2 and point 3, and also at point 1 to get reliable starting conditions and high statistics enough. And so this summarizes section 9, and again I won't read these aloud, but I'll leave you a moment to read it yourself, and if you have a feeling you don't know this, then please go back and revisit the material. And the last point is sort of this most important one, that this is not a mature field. There is intense and very exciting research going on the topic.